Okay, today we shall go on to gravitation. We have finished circular motion, so let's stop going around in circles. Okay, so let's move out of circle and move on to something else. And today we're going to do something like what I said, attractive, which is called gravitational pull. And Newton, there is this myth that says that he sat under an apple tree and then an apple fell onto him and then they thought of the thing. But actually it's not. Actually it's not. That's the myth. That's totally a myth. There's another myth about him building this bridge. I wouldn't call it a myth, actually it exists. There's this bridge that he built in Cambridge that doesn't require a single nail or bolt. It is still there apparently, but now there is a bolt. There are bolts and nails. Why? Because a smart aleck tried to take it apart and reconstruct it again, he couldn't. Yeah, so eventually they had to put nuts and bolts and nails onto the bridge. So right now, if you go to Cambridge, the bridge is still there. There are things holding the bridge together. Yeah? So why look at him? Is there a reason? Cambridge. Oh my goodness, why didn't I see that? Okay, so what Newton came up with, which is really important, really important, and that is so important because it is the fundamental of gravitation and the study of the universe. You must understand how powerful it is. It is something that works even if you are 5,000 light years away. It works. That's so powerful. Even when you cannot even see the star, it works on the star. So that's how powerful a law is when it works far beyond where you are. All right? Now there is of course some clause. When it gets very close, when you get very close to the major stars, big stars, that's when this breaks down. And guess what law kicks in? General theory of relativity. Yes, correct. Now, just a quick one. Scientists found that when they try to apply this to explain the motion of Mercury, is it Mercury or Venus? The closest one to Sun is Mercury, I think. Yeah, correct, Mercury. So when they try to apply this to Mercury to understand the motion of Mercury, they find that it actually differs by a certain time. The prediction and the actual measurement differs. So this is no longer true near very massive star. And that's why Mercury, it doesn't work for it because it's the closest. So that's when this kicks in. But I'm not going to go through this with you because I got to go through a module in math called tensors. Tensor. If you are interested, go and read up on it. Tensor. It's a field of math that you need to learn that to understand the general relativity in full glory. So, but this is the theory that kicks in if this does not apply anymore. But no worries, we are going to focus only on this. All right. So why don't we all get attracted together? Since anyone that has mass should exert a gravitational force on everyone else, right? So when we come into the class, we should just be there. Right? Because the mass is too small, and the other thing is that this constant is only 6.67 times 10 to the power minus 11. So let's see what's the force of gravitation between us at this scale that we're talking about. So let's say the gravitational force between Elia and Heng. Ken, let's see how attracted you are to each other. Let's guess Heng's mass. 60 kg? No, it's 60 lah. You do 65 lah. Ken? Earlier, gentlemen, whenever you guess the mass of a girl, the number that pops out in your mind minus 10 before you say it. So, Earlier, 35, I guess. So that distance is about, say, 3 meters. Ken? So can you just calculate the force? Just quickly, so you find out how attracted they are to each other. So what's the force of gravitation? Times 10 to the power minus something like confirm.
1.69 times 10 to the power of
negative 8. Confirm? Yeah. Confirm? 8 newtons. Now this is really small, right? I mean, a strand of hair, guess how heavy it is? Guess. A strand of hair. A guy's hair. Doesn't matter lah. Let's say Hannah's hair, longest I think over here. How heavy? 1 gram? 1 gram? Less than 1 gram? Less than 1 gram, right? So I say probably between 0.1 gram to 0.01 gram, that range. So let's say 0.05 grams. So 0.05 grams is about 0.05 times 10 to the power of minus 5 kg. If you talk about the weight of this is about 5 times 10 to the power of minus 4 newtons. Look at this and look at this. And that's why the two of them don't fly together. Can? So you're safe. Yeah. You're safe. So there's actually frictional force holding the two of you on the ground. So that's why you don't fly together. Can? Cool. But given if you're in outer space and if you stay there long enough, after infinite number of years, you'll slowly drift together. Okay, can? So that's why you don't come together, because the order of magnitude of force is too small. And over here on Earth, we have frictional forces. That's why you don't come together, fortunately. Now I'm going to give you something more difficult. It is still testing you on this, but more difficult mathematically. So what's the math problem I'm going to give you? Say, for example, if you've got two spherical objects, they are made of iron. Anyone knows what's the density of iron? Come on. Come on. Seriously. 1005? More. 1005 is only the density, 50% more than the density of water. Can't be, right? Make another guess. Anyone else? Some more. It's actually about 5,000 kg per meter cube. By the way, do you know what's the densest material on Earth? How dense the material is? Uranium, no. Actually, uranium is not very dense. Lead, no. There's a reason why lead is used for... mercury is the densest fluid on Earth. Platinum, actually. Okay, let's not go to outer space. Relax. We're not going there. Naturally occurring element, not black hole. Yeah, let's not go into that hole. So the thing is, density is about 5,000 kg, but the densest readily available thing sometimes found on rings, platinum, 21,000 kg per meter cube. Yeah, 21,000. One of the densest. The densest is I think 22,000. But it's a weird metal, rare metal. So density of iron 5,000 kg per meter cube. In case you don't know, the density of Earth is also about here, because the Earth is actually one big ball of iron, yeah, in the core. So I want you to find the radius such that the force of attraction between the two balls is 1 Newton. Give it a try. Be very careful, huh? Be very careful. There are booby traps in this question. Be very careful. Be very careful, because identical balls. I'm trying to use this example to surface something important, which none of you have asked up to now. Exactly. I was waiting for someone to ask that. Good one, Hannah. The R in that equation, guess what R it is? Is it the radius? Distance between what? Center of mass. Be very careful, center of mass over here and over here. Now, before you carry on with the question, let's discuss one point. Is the center of mass and center of gravity the same point? Is the center of mass and center of gravity the same point? Since we talk about center of mass. By the way, this is the distance between center of mass. But is the center of gravity, center of mass equivalent? Yes or no? How many? Okay, let's by gut sense. How many of you say yes, they are the same? Okay, can. How many of you say no? How many of you in outer space right now? Okay, right. The answer is no, they are not necessarily the same. Why? Let me give you a scenario. If you got a piece of metal, imagine side A and side B. Imagine the gravitational field on A is much stronger than the gravitational field on B. Do you agree that even though this mass over here, which is a uniform mass, the center of mass should be here? Uniform mass. The center of mass is right at the center. But because the gravitational pull over here is very strong compared to here, do you agree that the weight will be shifted here? So the center of gravity will be towards the left. Therefore, the center of mass and center of gravity will be the same point if it's uniform. Yes, correct. Okay? So be aware of this assumption. Most of the time, it's uniform. But if you're near the black hole, our favorite place on Earth, the black hole, yes, it will vary a lot over short distances. Now, come back to this question. Find the radius for me. Remembering what Hannah just now asked just now, that the r over there is the distance between the center of masses. Be very careful, huh? Be very careful what you substitute. When I ask this question to most students, it'll take 2 tries to get the answer. Let's see whether you can get it in one. What's the r? What's the radius of the ball? So that the force of attraction between the 2 balls will be 1 Newton. Yep. 4/3 pi r cube. Yes, correct. Forgotten your A-level math already. No, not A-level, O-level math. Your Sec 4 math. What's the volume of a cone? 2/3? 1/3 pi r square h. Yeah. Yeah. Anyone got an answer already? Go, go, go. Do you use, okay, do you use square root, do you perform the necessary square roots? A hint for you, you got to square root it twice. You should have an r to the power of 4. I think it's about there, yes. I think it's about there. Congratulations, let's check. So 1 is equals to 6.67 times 10 to the power minus 11 times 4/3 pi r cubed rho square divided by 2r whole thing square. That's correct. So it's 6.67 times 10 to the power minus 11, 16 over 9 pi squared r6 rho square, 4r square. So this cancels with this 4, this cancels with this 4. So r to the power 4 is equals to 9 over 6.67 times 10 to the power minus 11 times pi squared rho square, square root of this one. Now, if you do the necessary calculation, you should get the answer. Did I miss out anything? I think I missed out 4. There should be a 4. If you perform square root, you should square root it twice. Because you square root once, you get a r square, you square it another time to get it as r. Okay? For those of you who have already finished this and your answer is 3 point something? 4 point something? It should be around that order. 4 point? 3 point what? 3 point what? 3.2. 3.4. 3.42. Okay. Okay, about there. I remember the answer to be about 3 point something. Cool. Okay. Now, for those of you who have finished this and feel that you need something more intellectually stimulating, think about this, which I'll go on in the additional module, the advanced module of the next lesson probably. How do you find the force of this rod? How do you find the collective force, the total force of this rod? Make a guess. Do you need integration? You need, right? Why? Because at different distances, you have different force, right? You figure out today, how are you going to apply integration through all the experiences, the very pleasant experiences you have with integration? How do you apply it to this scenario? I'll go through this tomorrow. But before that, I want you to prep your mind. how would you have done it? How do you integrate to find the collective force by this m over here on this m over here when this is r and this is 2r, say for example? How do you find the force on this rod? And we'll do different permutation. In the advanced module, we'll talk about the force. How about on this? Yeah? Think about this, Ken. Think about this. Prep your mind for whatever we're going to do on this, Ken. So I'll leave it here. But I will go on to something that is more IB today. Take a look at this. Is there something over here? No, nothing. Is there something over here? This is quite TOK question now. Is there something over there? Is there something? Okay. Is there something over here? Is there something over here? Come on! This is not a trick, it's a smudge. Yeah, it's a dot. No, is there something over here? If this is outer space, is there something over here? It's like, this is my screwing.
Define something.
Define something. It is a very interesting question. You see, if there is nothing over there, let's go by the other way of argument. If there is nothing over there, and I place a mass over here, then why would it experience a force there? Why does it experience a force there if there is nothing over there? So there must be something over there such that if I place a mass over there, that mass interact with that something over there that causes it to experience a force. You agree? See, there is gravitational field over here, right? We can't see it, we can feel it, and there's a force. So how do we find out how strong the gravitational field is? We can't say that there's nothing over there, so we can't know. So how we define gravitational field strength? The strength of a field is to put a 1 kg mass there. The force on that 1 kg mass there is what we call gravitational field strength. Okay? I think we had this discussion some time ago. Empty space is not that empty after all. Yeah? Particles, antiparticles pop up everywhere. So what do we mean by something? Empty space is actually not very empty. Yeah? Okay. So therefore, gravitational field strength, which is defined by, the symbol for gravitational field strength is G, which is equals to Gm times 1 upon r squared, which is Gm upon r squared. So this is an important equation. It is defined as the force per unit mass on a point mass. Now, if on your notes, can you please highlight the word point mass or test mass or whichever that they mentioned over there? Because what students tend to miss out on the exam paper is not force per unit mass. Most students will remember force per unit mass, which is F upon m. But what most students will miss out is on a point mass. And I marked IB papers before. IB specifically put in the mark scheme say mark down or minus 1 mark, or don't give that 1 mark if the student missed out the point mass. So you must remember the point mass. Now, we shouldn't remember things because it is in the syllabus, because it is something that we need to remember. The question is, why is it important for it to be a point mass? By the way, do you know what it means to be a point mass? What does it mean? A point mass doesn't have something. What's the something? Volume, exactly. So a point mass is a mass that is defined as something that has negligible volume. But then if it has negligible volume or it has no volume, then it doesn't exist. What? Oh, this is the okay. So something of negligible volume, not no volume. So negligible volume can be compared to Earth, we are negligible. So the idea of a point mass is negligible, not no mass, no volume. And the reason why we need it to be a point mass is because if we have Earth over here and we have a humongous mass over here, do you agree that this mass over here is going to influence the gravitational field due to the Earth? So that's why we need a point mass, so that it has no influence on the gravitational field due to the parent mass. That's the reason why. If it is not a point mass, if it has a volume, the field strength over here will change because there is volume over here. All right? Make a guess. Is field strength a vector quantity or a scalar quantity? Why? Because it is related to? Because it is related to? Force, exactly. So you need to remember that field strength is a vector quantity. Now, I'm going to give you a question that's going to test your understanding of applying vectors. Let's see whether you understand. Any one of you know what is the mass of the moon relative to Earth? If the mass of the moon, if the mass of Earth is m, what is the mass of moon? Come on, our nearest neighbor. How can you not know such a beautiful thing on the sky? No, that is g. The g on moon is 6 times smaller. Yeah, that's why astronauts, do you know the astronaut suit that they wear is about 120 kg. So that's why even though it's 120 kg, they can hop around on moon because it only weighs 20 kg. But what about the mass? Anyone? Make a guess. Sorry? 1/3. No. Much smaller. Square of that. Yeah, square of that. Yes, square of that. It's actually m upon 81. Amazing, right? But even though this m upon 81, do you know what's the effect if moon is not there? Yeah, no tides at all. If the moon were to suddenly go away, what happened is that the whole ocean of the Earth is going to go into this humongous oscillation, which means the tide is going to go as high as probably some buildings on one side of the Earth. And the other side of Earth, there will be no like water kind of thing. So it's actually the moon's presence stabilizes the ocean in our sea. So it has a stabilizing effect. Though it slows down, the moon slows down, because of the tidal effect, it slows down our Earth rotation by a few seconds every century. Do you know that Earth's rotational period wasn't 24 hours? Earth's rotational period at the near formation period, do you know how short it was? Do you know how short it was? Come on. 1 hour, everything will fly off the surface of Earth already. It's about 21 hours. So it's slowed down over the years, yeah, to 24 hours. So what I want you to do is this. If this is L, can you find a point over here where the G resultant is equal to 0? I want you to find X in terms of L, meaning that X upon L equals to a number. What's the number? Give it a try. It's also a mathematically rather demanding one. Let's see whether you are a smart mathematician or hardworking mathematician. Because there are two ways of doing these questions. Okay, now Eden, you look more bored than usual. In case you wonder whether the number is a complex number and then some SERPs, no, it's a nice number. It's a rather nice number. Define nice, that means you can put it as integer over integer. Yeah, a rather nice number. Let's take a walk and see how you're doing. You should have two equations and you need to solve for one unknown. The resultant field due to both the Earth and the Moon. That means the Moon is pulling towards the right, the Earth is pulling towards the left. Yeah. Anyone got an answer? 1 over? Yes, correct. 0.1 L. 0.1 L. The way to go about this is gm upon L minus x squared equals to gm upon 81 divided by x squared. Gm cancels off. L minus x upon x squared is equals to 81. Okay? Yeah. The hardworking ones will expand the thing and then, yeah. The hardworking ones will expand here. That means L squared minus 2LX plus x squared. That will be the hardworking way. Yeah. You still get the same answer. Anyone remember which Apollo mission is the first mission that landed on moon? Human, yeah, 11. Yep, 11 was the first one. And when Apollo 11 went to moon, they followed a path that looks like this. Why? Why not? Why go round and then round? Figure 8. Sorry? Gravitational slingshot, that's what you're saying, gravitational slingshot. Yes and no, but usually gravitational slingshot, you use it when you want to go interplanet. Yeah, interplanetary travel. But this one is for another reason. Yeah. I'll leave it as it is. The answer will be given to you at the later part of the topic. Okay, so think about this. Why does it go in a figure of 8? Why not just go direct? It's a shorter path, right? Why go the long path? And when you think NASA, they always try to minimize cost because they want to minimize fuel. And how do you do that? They minimize fuel. And why is it that this requires less fuel than this? Think about this, Ken? And also the next thing I want you to think about is, remember this one, and this one. Ken? So do think about these two questions. We will answer this first, and then at the later part of the topic, we'll answer this one. Cool? And that's it for today. The field strength and force, that's the two things I want you to remember. Tomorrow lesson, we'll cover this one and we'll cover the situation which none of you have actually asked up to now. We talk about gm upon r squared and we always assume that the point is, we talk about here, and then we always talk about gm upon r squared where r is point mass, yes, but look at this. We always assume that the r is bigger than? Exactly. What if we go into the earth? What if it is at the center of the earth? Think about this, The answers will be unraveled tomorrow lesson. Ken, think about all these questions.